The speed of light is a lie. We found the glitch in Einstein's code. The neutrinos rang first. Pagers buzzed on kitchen tables in 3 countries, and in one basement lab a printer spat out numbers nobody expected to see until morning. Outside, the large Magellanic Cloud glowed like a faint bruise. Inside, clocks disagreed by seconds that felt like verdicts. They told us light is the referee of time, the fastest messenger, the law itself. But that night the sky sent an earlier whisper. The key to the wall had been sitting in plain sight, buried under expected and filed away. If the wall is a setting, not a law, everything else we teach bends. To see the key, rewind. The night the sky blinked, SN 1987A. It's February 23, 1987, before sunrise in Japan. Under a mountain, Kamiok and II hums, waiting for ghosts. Across the Pacific, IMB near Cleveland listens too. In Italy, the Mont Blanc LSD detector keeps its vigil. Then, for a few moments, the ghosts arrive. Here, why it matters. Every GPS route, every interplanetary trajectory, the way we measure cosmic distances, all assume that when something happens out there, light defines when we learn it happened. If that clock slips, our map kinks. How far, how old, how fast becomes according to which messenger. In the large Magellanic Cloud, a blue supergiant's core collapses. The implosion rebounds, launching a shock. Deep inside, neutrinos flood outward, trillions, nearly indifferent to matter. Photons, born into chaos, ricochet through dense layers, trapped until the shock reaches the surface. On Earth, Kamiok and II records 12 events within seconds. IMB logs 8. Baxen in the Caucasus adds 5. Roughly 24 neutrinos in total, laughably few compared to the torrent that passed through us, but enough to mark the moment. Hours later, telescopes catch the light. A new star in the LMC, soon named SN 1987A. On paper, this is fine. Neutrinos should beat photons out of the star because photons scatter while neutrinos don't. The observed offset, neutrino burst first, optical brightening later by several hours, fits supernova models where neutrino emission comes milliseconds after core bounce and light waits for shock breakout. Relativity isn't threatened, but the hardware story adds seams. We're stitching arrivals across continents without a universal clock to nanoseconds. The two-way speed of light sets our rulers. The one-way path leans on synchronization assumptions most people never notice. Meanwhile, the human scramble turns the abstract into breath. In Japan, pagers rattle ceramic plates at breakfast. A graduate student sprints to the underground control room, heart-punching ribs. In Ohio, a physicist skids down a corridor in socks, a dot matrix printout still warm in his hand. "This is real," he says, to no one in particular. In Italy, the Mont Blanc team points to an earlier cluster, events about 4 hours before the others, and arguments ignite about timing and backgrounds. Later audits will dim the Mont Blanc claim's certainty, but in the moment, the world is awake. The gap stakes sharpen with perspective. If our cosmic clocks are a braid, neutrinos, photons, and later gravitational waves, then simultaneous is an instrument choice, not a gift from the sky. When the choice moves, so do conclusions. Which messenger sets zero? While neutrino plots circulate by fax, amateur astronomers in the southern hemisphere notice a pinpoint brightening in the Tarantula region. Observatory domes grind open. Spectra confirm a Type II supernova from a blue supergiant. Unusual. A B3 star that didn't shed its envelope the way textbooks expected. Over weeks, the light curve rises, plateaus, then fades. A triple-ring structure around the progenitor begins to glow as the blast wave energizes circumstellar material. SN 1987, A becomes the most studied supernova in modern history. Years later, its neutrinos anchor something bigger, multi-messenger astronomy. Photons, neutrinos, and eventually gravitational waves must line up into a single story. If any arrival refuses reconciliation, the mismatch isn't a footnote, it's a crack in our model of time. In 1987, gravitational wave detectors aren't ready. Their era is decades away. But the template forms. Different messengers leave at different times, traverse different effective media, and demand a shared narrative pinned by clocks we synchronize with light. And that's the scene. Distant clocks don't sync themselves. Einstein gave us a rule in 1905. Split the round-trip light time evenly to set simultaneity. It's practical, elegant, and a convention. We measure the two-way speed of light exquisitely, the one-way speed we import by that synchronization. When Kamiokand and IMB compare timestamps, they trust local calibrations and conversions tied, ultimately, to that rule. It works because the world is kind. But a working convention is still a choice. Micro-stories keep the beat. In Japan, someone pins burst at 7:35 on a corkboard and draws a smiley face, then crosses it out like the joke felt too loud for the day. In Ohio, a grad student phones home. "We caught it." His mom asks, "Caught what?" He pauses, not sure where to start. In Italy, a cafeteria order for more coffee turns into a calculation on a napkin, arrows and sigmas crowding the stains. Was light late or were neutrinos early? Both and neither. Neutrinos left promptly from deep inside. Light emerged later from the surface. The difference isn't a broken limit, it's channel physics. Yet the night exposes how our certainty is built. We align clocks with light, then use those clocks to declare light the referee. For round trips, nature agrees every time. For one-way comparisons across the sky, we lean on a definition because it makes the math sing and the missions fly. And while telescopes watched the rings of 1987 Brighton, our own machines drifting into the dark began to whisper something else. Tiny Doppler drifts and timing nudges that refused to disappear into the error bars. The neutrinos had opened the door. The spacecraft would invite us in. The drift that shouldn't exist, the pioneer anomaly. Meanwhile, our own machines were still talking to us from the dark. Pioneer 10 and 11, launched in the early 197s, slipped past Jupiter, skimmed Saturn's domain and headed outward with nothing but radio as a lifeline. That radio tone was a heartbeat and a ruler in one. You ping a probe, it transpons the signal back, and the two-way Doppler shift tells you its line-of-sight speed to parts per trillion. Over years, those parts per trillion become miles of error or victory. Here's why this matters. Deep space navigation is trust made mechanical. One missed force, one unmodeled delay, and a billion-dollar mission can skim the wrong hemisphere. The deep space network times the round trip and builds a world from those numbers. If something nudges the path or biases the tone, you won't see a mystery. You'll see a residual that refuses to flap. By the late 198s and through the 199s, analysts at JPL and elsewhere noticed a sliver of stubborn blue creeping into the Pioneer data. The Doppler residuals looked as if the spacecraft were experiencing a tiny, constant sunward acceleration, about 8.7 times 10 meters per second squared. Not a shove, a whisper. You wouldn't feel it in a car. Over billions of kilometers, it adds up. The checklist began. Solar radiation pressure pushes on the big dish. Model it better. Gravity from planets, the Kuiper belt, even general relativity's small corrections, include them all. Outgassing from thruster seals, maybe. Spin rate changes coupling to dynamics, perhaps. Then the engineer's favorite culprit, heat. Pioneer's radioisotope thermoelectric generators ran hot. If infrared photons radiated asymmetrically, say, bouncing off the back of the high-gain antenna, they could create a steady recoil. Warmth turned into thrust. For a while, the anomaly sharpened as more data came in. Papers speculated about modified gravity beyond Saturn, moan-like behavior in the outer solar system, drag from dust or dark matter. Others counseled patience. Spacecraft are messy. Clean up the housekeeping before rewriting physics. That became a campaign. Old telemetry tapes were baked and digitized. Attitude histories were reconstructed. Every watt of heat was traced from source to radiator. Teams built finite element thermal models and translated temperature histories into micronewtons. The thermal recoil solution gathered weight. Analyses showed that asymmetric heat emission could account for most, and in some reconstructions nearly all, of the 8.7 times 10 ms2. The leftover slivers wavered inside uncertainties tied to material aging and surface properties no one measured in deep space. The official mood settled. Not a new force, just a spacecraft telling us exactly how hard it was sweating. But even victory had seams. The models depended on assumptions about emissivity changing over decades, dust accumulating, spin axis precession, and complex reflections off braces and booms. Small correlations in the data, wiggles tied to Earth's rotation, station handovers, or Sun-Earth probe geometry, didn't always flatten completely. In hallways, you'd hear, "I'm 95% convinced it's heat," delivered with a smile that left room for the last 5. Then Earth flybys started whispering too. A handful of planetary encounters in the 199s and 200s returned tiny velocity mismatches, millimeters per second after gravity assists. Some flybys showed nothing. Others showed an energy change that didn't wash away with standard models. Analysts plotted declinations and azimuths, mapped tracking station transitions, and chased relativity corrections. Patterns teased, then slipped. Explanations ranged from modeling subtleties in Earth's gravity field and atmosphere to transponder frequency ramping and signal path calibration. The effect never rose to Pioneer's celebrity, but it kept the question alive. Are our signal models hiding edges? Here's the seam under the storyline. Two-way Doppler is a round-trip story. Earth sends a carrier. The spacecraft multiplies the uplink by a fixed ratio and sends it back. We compare the received frequency to the station clock. The beauty of two-way tracking is that it cancels a lot of one-way sins, independent clock drifts, some path delays and asymmetries. But it also buries the one-way path. If something subtle biases the outbound or inbound leg differently, ionosphere, troposphere, station electronics, or even our convention for aligning clocks, the round trip can look clean while the one-way hides a wrinkle we never measured directly. Human moments gave the anomaly its face. A navigation lead near Goldstone at 2 a.m., socks off in a motel room, stared at a residual plot that wouldn't lie flat, thought about his kid's spelling test, and shut the laptop, only to dream in hertz. A young analyst spent weekends coaxing bits off magnetic tapes older than she was, labeling each file like a museum curator. In a conference coffee line, an old-timer muttered, "Space punishes certainty," and 3 people nodded like it was a prayer. In the end, Pioneer taught humility and craft. The best answer is that thermal recoil drove a steady sunward push of roughly the observed magnitude, with uncertainties that account for the rest. The flyby anomalies likely fold into station geometry, modeling choices, and small systematics that vanish as measurement campaigns improve. But the residue left a mark. Our navigation triumphs rest on exquisitely modeled physics and a quiet assumption. Two-way timing rules everything we trust, while the one-way path is a convention dressed as a constant. And that's why the neutrino night mattered. Different messengers, different channels, different buffers. Our instruments choose a zero and build a universe around it. Pioneer's whisper didn't break the limit. It pressed on the seam where we translate round-trip tones into one-way stories. Across town, in quieter labs, something even stranger was forming. Pairs of particles coordinating across distance as if a message had flown between them, without a message at all. The instant that isn't quantum entanglement's nasty habit. Across town from the deep space dishes, a different kind of antenna was waiting. Silicon avalanche photodiodes counting single photons. Each click the softest footstep a particle can make. 2 nonlinear crystals, 1 pump laser and the strangest pact in physics, create a pair, send them apart, and ask questions they aren't supposed to answer until they've compared notes. Stakes first. Locality is the bedtime story that lets us sleep. What happens here can't depend on a choice made over there right now. Entanglement looked at that story and shrugged. Einstein, Podolsky, and Rosen set the chessboard in 1935. If quantum mechanics is complete, Then distant particles share a state that makes their outcomes correlate too well, so well it feels like they're coordinating instantly. If that's absurd, there must be hidden instructions tucked into each particle at the start. 3 decades later, John Bell turned the debate into math. He wrote inequalities that any local hidden instruction theory must obey. Build an experiment that violates them, and the universe has to surrender either locality, realism, or both. Laboratories obliged. In the 198s, Elaine Aspect's team sent entangled photons through fast-switching analyzers, changing settings while the photons were already in flight. The results violated Bell's inequality. Critics pointed to loopholes. Maybe the sample was biased because detectors missed most photons, the detection loophole. Maybe the switching wasn't fast enough to prevent a slow, subliminal leak of information, the locality loophole. The response became a campaign. Better sources, brighter pairs, faster and space-like separated setting choices. By the mid-2001s, loophole-free became a deliverable. In Delft, experimenters entangled electron spins in diamond, read them out with high efficiency, and chose measurement settings fast enough and far enough apart to seal the locality gap. In Boulder and Vienna, photonic tests paired ultra-low-loss optics with superconducting detectors, shutting the detection loophole in the same runs where geometry sealed locality. The correlations refused to fit any local hidden variable script. Bell's inequality wasn't just broken, it was broken clean. Here's the nasty habit. Outcomes correlate across space-like separation, as if an update flashed between the labs. Yet messaging faster than light stays impossible. No signaling theorems say the marginal statistics on one side don't change when you twiddle settings on the other. You only see the pattern after a slow, classical comparison, and that comparison obeys C relativity survives. But every dataset looks like a conspiracy that cleans up after itself before you can catch it. Now the seam that ties back to our clocks. To call two detections coincidences, you need synchronized time tags. To prove the labs are space-like separated, you draw light cones using a C you only measure in round trips. The one-way alignment is a convention, Einstein's rule to split round-trip time evenly baked into your timing network. It works because the world is kind and the equipment is honest. But the bookkeeping reminds you, even here, simultaneity is negotiated, not discovered. Human beats kept the theory grounded. A grad student in a dark lab taped a note over a big red laser-on button that just said, "Breathe." A pi sent an email at 2:13 a.m. "We're over 5 sigma." A satellite pass for a free space link cleared. Someone cried from relief more than discovery. Later, teams used starlight from distant quasars to choose analyzer settings, pushing any possible collusion with hidden variables back hundreds of years. Cosmic randomness became part of the circuit diagram. The payoff escaped philosophy fast. Quantum key distribution turned entanglement's correlations into security. Tamper with the link and the error rate climbs. Teleportation protocols moved quantum states between nodes without moving particles, using pre-shared entanglement plus a classical message. Entanglement swapping stitched independent links into longer chains, the basis for quantum repeaters. Networks started to look like preloaded scaffolding. Pay up front in entangled pairs. Spend later when the classical sidecar arrives at light speed with the decoding key. Complication stayed honest. No signaling relies on assumptions. Independent setting choices, clean space-like separation, detectors free of bias. Loophole-free tests nailed them simultaneously, but never absolutely. There's always a residual someone can try to pry open. Philosophers reminded everyone about freedom of choice, the axiom that your random setting isn't secretly correlated with hidden variables. Cosmic photon randomizers helped, not because they prove independence in some cosmic court, but because they make any conspiracy absurdly baroque. Meanwhile, jargon hit a simple tension. We say no influence because no controllable message outruns light, yet the joint state acts like constraint rather than courier. Precompiled correlations make local updates land as if the world coordinated on a beat outside our messaging budget. If C is a refresh limit, entanglement is structure, the kind you install before the beat, then reveal after the beat when notes are compared. Microstories kept the 30-second rule alive. A postdoc set an alarm for a 3:07 a.m. satellite pass and whispered, "Come on," to her phone's live plot of coincidence rates. Another team broke into applause when their time tag jitter calibration finally held at tens of picoseconds. A philosopher brought muffins and left with more questions than crumbs. The field moved from spooky to service-level agreements. How many bell pairs per second at this fidelity, under this weather, across this baseline? This was the moment the instant that tisn't stopped feeling like a paradox and started looking like architecture. No bits move faster than light. Patterns do, in a sense that lives in correlations pre-installed across space, only readable after slow notes align. Our clocks, synchronized by a convention that works, sort coincidences into meaning. The wall stands for messages. The seam appears in how we define now to read the pattern. And that seam is about to matter even more when we talk about the rule that smuggled itself into our timing from the start. The assumption Einstein needed, one-way versus two-way light. To see why the instant that tisn't keeps getting away with it, we have to open the box almost nobody touches. There are two speeds of light hiding inside one symbol. The two-way speed, the outtan back you get from a ping and a reflection, is what we actually measure. The one-way speed, the straight shot from A to B, is what we assume when we set clocks. That move wasn't a loophole, it was Einstein's genius. It's also the seam the story keeps snagging on. In 1905, Einstein needed a clean way to glue distant events into a single timeline. He proposed a rule that feels obvious until you look closely. Synchronize clocks by sending a light pulse from A to B and back. Then set the clocks so that the travel time is split evenly between the outbound and inbound legs. If the round trip takes t, you declare the one-way times t2 and t2. That choice, Einstein's synchronization, bakes in that the one-way speed equals the measured two-way speed, c, in all directions. Philosophers later gave that choice a dial. Hans Reichenbach introduced epsilon, a parameter that tells you how to split the round trip. Epsilon equals 1,2 gives Einstein's symmetric split. Tilt epsilon away from 1,2 and you skew simultaneous in a direction-dependent way, while keeping the same round trip c and the same local physics. If you rewrite all your equations consistently, observables tied to round trips don't change. You get the same experiment, the same radar distance, the same Doppler tracking. The world doesn't move, the bookkeeping does. Why should anyone care? Because our hardest problems ride on clocks. GPS works by comparing one-way signal times from satellites to a receiver down here. But under the hood, it's built to cancel the traps. It solves for receiver time bias, uses relativistic models for satellite clocks, and relies on a constellation tied to a global coordinate time defined by Einstein synchronization. Time transfer between national labs, fiber links, and satellite common view all inherit that same convention. It's not wrong. It's a standard. Standards are how the world functions, but standards are also choices. Here's the stakes in practice. Every time you call two detections simultaneous, you've already picked a way to align the tapes. Entanglement experiments trust picosecond time tags that were disciplined by a network using Einstein's rule. Neutrino burst comparisons between continents translate local times through GPS and geodesy into a world clock that assumes symmetric one-way light. Deep space navigation lives on two-way tracking, but when you cross-compare stations or fold in one-way ranging and time transfer, you step onto the same convention. Our universe of data is stitched together on a principle we chose because it makes the math sing and the missions fly. The predictable objection is right and misleading at the same time. If epsilon is just a convention, then nothing physical depends on it. True for round-trip observables, true for any local lab in free fall. But the interpretation of distant order, the sequence you write into the script when you say event A happened before, Event B across the sky leans on the slice you picked. Special relativity tells you not to treat distant simultaneity as a fact of nature, it's coordination. Einstein's move made that coordination simple and isotropic. That simplicity feels like truth because it works everywhere we've looked. Metrologists live in this world daily. They fight picoseconds of dispersion in fibers. Forward and backward paths aren't identical. They calibrate two-way satellite time and frequency transfer to nanoseconds, while one-way delays soak up models of troposphere and ionosphere that don't perfectly mirror. In their notebooks, you'll find lines like assume symmetry to first order, residual asymmetry below XPS. It's honest, and it keeps the trains on time. It also marks the seam. We can measure the out and back. We can only define the straight shot. Human moments make the point stick. In a timing lab, two hydrogen masers sit like quiet metronomes. A technician routes a 10 MHz reference through kilometers of buried fiber and discovers the forward path lags the return by a hair. A colleague adds a dispersion compensator and writes assume symmetry in the log. They both know that assumption is the move that keeps the network sane. It's also where reality leans on a promise we make to ourselves. Now tie this back to the threads we've been pulling. SN 1987A's neutrinos beat the light not by breaking C, but by leaving first and traveling differently. To compare arrivals, we mapped local clocks into a global time by Einstein's rule. The story holds because supernova physics and good synchronization agree. Pioneer's Doppler residuals were a two-way triumph, translating them into where the probe is right now, folds in Earth orientation, station locations, media delays, and the same synchronization underneath. Quantum Bell tests sort coincidences by time tags disciplined under that convention and overlay light cones drawn with a C we know from round trips. None of this undermines relativity. It strengthens it by making the contract explicit. The invariant content, the stuff no coordinate choice can touch, is built from local measurements and round trips. The seductive content, now across the galaxy, instant coordination, earlier by hours, rides on how we chose to set distant clocks. That's the glitch worth naming, not a broken wall, a seam. The speed of light is a hard budget for messages you can control. The one-way value that lets you line up distant tapes is a definition that has never betrayed us, and might never, but remains a definition. There's a reason textbooks keep this in the basement. In careful hands, it's unexciting. Change epsilon everywhere and you get the same answers. In clumsy hands, it sounds like license to say anything. We're not throwing a party for ambiguity. We're putting a label on the contract we signed in 1905 so we can recognize it when anomalies press on the edges. Because the next arenas, horizons that look like render boundaries and vacuums that aren't empty, depend on how the budget is enforced, not on breaking it. The wall as a refresh rate, computational universe framing. So here's the turn that makes the seam useful. Stop treating C like a moody traffic cop and start seeing it like a system budget, bandwidth, latency, throughput. If reality computes, limits aren't proclamations, they're resource ceilings. Blow the budget and frames tear. Stay inside it and everything looks smooth enough to call law. Stakes first. A budget can be optimized. That's where routing around cost becomes a plan instead of a prayer. There's a lineage here. In the 196s, Rolf Landwehr nailed information to thermodynamics. Erase 1 bit, pay at least kT ln2 in heat. Information isn't ink, it leaves a thermal footprint. In the 199s, Norman Margolis and Lev Levitin linked energy to the maximum rate of orthogonal state transitions, roughly 2 EH operations per second. Give a system energy E, and there's a cap on how fast it can genuinely move to a distinguishable state. Those two together whisper a picture. If every finite region has finite energy and entropy, there's a ceiling on update speed and memory. The light cone starts to look like a dependency graph enforced by a global tick budget. Translate that into familiar physics without pretending there's a literal CPU. Fields update locally. Interactions propagate at finite speed. Lorentz symmetry is the compiler that keeps the code consistent. In that reading, c is the width of the bus connecting causally related updates. The front velocity that guards causality is the hard cap on when a controllable change can first appear. Anything that looks faster, phase velocity games, group velocity tricks, entanglements, instant-looking patterns, isn't a violation, it's caching, pre-computation, or compression showing through. Skeptics hear simulation and reach for a red pen. That's not required. Seth Lloyd's universe as quantum computer, Stephen Wolfram's rewriting systems, and Leonard Susskind's complexity as length aren't claims about teenagers rendering galaxies. They're claims that the laws we already trust are best understood as constraints on information processing. General relativity plus quantum field theory already enforce causal structure and finite signal speed. The computational framing is a different pair of glasses for the same scene. It highlights budgets and trade-offs you can exploit without changing the math that works. Human moments make it real. In a seminar room, someone writes KTLN2 beside a sketch of a black hole horizon and says, "Erase here, pay there." A colleague circles 2EH and quips, "So that's the overtime policy." A grad student draws a light cone and writes dependency DAG, then grins because the joke landed in a room that shouldn't find it funny. What matters is the shared instinct. Limits are resources. Resources can be scheduled. Now put gravity into the conversation. Black holes carry entropy proportional to their horizon area. The Bekenstein bound caps the information in a region by its energy and size. Holography says bulk physics can be encoded on a boundary. Susskind and collaborators go further. The interior volume behind a horizon seems to track the quantum complexity of the boundary state, the minimal number of simple gates needed to build it. Complexity, in that sense, acts like an internal clock. It grows linearly for a long time, pacing what the interior can do without any superluminal courier. The refresh budget is enforced both locally by C and globally by how hard it is to rewrite the state. That reframes our earlier seams. Entanglement's instant isn't a courier sprinting outside the cone. It's precompiled constraint across a shared state that only becomes actionable when a classical note arrives at light speed. SN 1987, A staggered messengers look like channels with different buffering and access rules. Neutrinos punching out on a low-latency path. Photons waiting for a congested surface to clear gravitational waves. Had we caught them then? Radiating straight from quadrupole dynamics. Pioneer's Doppler saga becomes a parable about reading a compiled interface, two-way timing, while forgetting you don't see the source code, the one-way path you define by convention. If C is the refresh rate, where do glitches hide? Near render boundaries, horizons, strong curvature, places where the scheduler runs hot. That's where thermodynamic analogies stop being analogies. Hawking radiation isn't a metaphor. It's a budget reconciliation between field fluctuations and gravity's bookkeeping. Islands and entanglement wedges aren't literary flourishes. They're instructions for where the code that reconstructs interior actually lives. No signal outruns C. Meaning moves by code reassigning what counts as where when enough radiation accumulates. The vacuum's not empty in this framing either. It's the default workload. Zero-point modes hum like background processes. Boundary conditions are like configuration files. Plates, cavities, or intense fields change which modes are available and how expensive they are to excite. The Scharnhorst calculation, phase velocity nudging above C between perfectly conducting plates, reads like a corner case performance quirk that never touches the front velocity. Engineers already do the terrestrial version with metamaterials. Shape effective geometry so waves take shorter coordinate paths while causality stays chained to C. And here's the payoff you can build around. If limits are budgets, progress looks like better scheduling. Precompute correlations with entanglement so the classical sidecar has less to do. Compress paths with geometry inside devices so you waste fewer ticks. Tune environment so the default workload stops eating your margin. The wall for controllable messages doesn't move. Your experience of cost does. That's not poetry, it's a design spec. One last human beat before we move on. A young team prototypes an analog horizon in a Bose-Einstein condensate and watches correlated excitations pop in pairs. Someone whispers, "It's just noise, right?" And another replies, "It's noise with a spectrum we asked for." On a whiteboard, someone writes, C equals bandwidth for action, entanglement equals structure for meaning. They underline action and meaning, not because they're soft words, but because they finally map to knobs you can turn without lying to physics or to people. Where theories collide, black holes, firewalls, and horizons. While we've been talking about budgets and refresh rates, horizons have been enforcing them with no room for negotiation. Stakes first. If quantum mechanics keeps information and general relativity keeps free fall boring at the horizon, then both can't stay naive. Unitarity says the book is never lost. Equivalence says you won't feel a wall crossing the line. Black holes made those promises collide. Start with the classic arc. A star collapses, curvature steepens, an event horizon forms, the boundary beyond which no message escapes. Stephen Hawking adds heat to the picture in the 197s. Quantum fields around the horizon radiate, pairs fluctuate, one partner falls, the other escapes. The black hole glows with a temperature set by surface gravity and slowly evaporates. The outgoing radiation looks thermal. Toss in a diary, wait eons, and what you get back reads like noise. If the hole vanishes, where did the diary's information go? For a while, the answer was a shrug wrapped in paradox. Then hints accumulated. Don Page calculated how the entropy of the radiation should evolve if unitarity holds. The Page curve rises at first, then turns over halfway through evaporation as correlations start to leak out. Holography raised the hint to a principle. In certain spacetimes, a quantum theory on a boundary encodes the entire bulk, horizon and all. If the boundary is unitary, so is the bulk. Information can't vanish. It has to be encoded in the radiation somehow, even if locally the horizon feels bland. Human beats kept the math honest. After a seminar, someone wipes chalk dust off a sleeve and admits they haven't slept well since reading the latest preprint. Another draws a Penrose diagram and circles the horizon like it's a crime scene. The hallway ends with coffee, not consensus. Then 2012 arrived with a jolt. The AMPS argument, Almary, Marolf, Polchinski, and Sully, took entanglement seriously enough to break something. Near the horizon, the vacuum looks calm only if outgoing modes are entangled with their infalling partners. But if information gets out, those same outgoing modes must be entangled with earlier radiation to carry the diary's details. Entanglement is monogamous. You can't max out with two different partners. Something has to give, either no drama at the horizon or unitarity. AMPS said, if you force unitarity, the horizon erupts into a firewall that incinerates anything crossing. The smooth doorway becomes a blast furnace. Impact was immediate. If firewalls are real, the equivalence principle fails at the one place we thought was boring. If they aren't, you need a mechanism that lets information out without double booking entanglement. Holography stepped back in with a refined dictionary. Using quantum extremal surfaces and what became known as the island formula, theorists computed entanglement entropy in semi-classical gravity and found Page curves that bend the right way. The trick wasn't a courier sprinting faster than light. It was redefining which region counts as outside for the purposes of reconstruction. As evaporation proceeds, an island behind the horizon is included in the radiation's entanglement wedge. The code that reconstructs the diary lives partly where naive geometry says, inside. Translated, locality stretches in a way coding theorists find familiar. The radiation doesn't carry a naked bit that left yesterday. It carries redundancy that only becomes readable after enough of it accumulates. No signal crosses a space-like gap. Causality stays chained to see meaning moves because the global state reassigns where the ledger lives. That's a render boundary move. The frame updates its asset map, while the interface for messages never breaks the budget. Skeptics weren't quiet. Words hiding work. A margin note asked next to island. Equations answered. Extremize generalized entropy over candidate surfaces. Pick the minimal one, compute. The match to unitarity wasn't hand-waving. It produced the page curve from gravitational path integrals in toy models. You can argue about regimes and approximations. You can't dismiss the direction. Horizons enforce budgets with code, not couriers. Here's where the computational framing earns its keep. If C is bandwidth for action and complexity is an internal clock, then a black hole is a place where the scheduler runs hot. The horizon's thermodynamics, temperature, entropy, evaporation, are the cost accounting. The firewall crisis forced us to confront just how the cost is paid, not by a forbidden superluminal message, but by encoding that makes inside versus outside a function of what you measure and when. The no-drama promise survives if you fall freely without trying to read global codes on the way down. The unitarity promise survives because the total ledger, properly defined, never loses a line. Human micro-stories kept the 30-second beat. A postdoc pointed at a curve finally turning over and clapped a hand over her mouth. Across campus, someone drew a tiny palm tree on an island in a diagram and laughed to keep from grinding their teeth. A referee returned a report that said, "Replace metaphor with mechanism," and got a new draft with both. This is the collision point our scene predicted. No faster-than-light messages appear. The wall stands. But the meaning of where at a horizon is coded in global correlations that only become accessible within the light speed budget. Render boundaries police action. Code moves meaning. If you're looking for a glitch, it's not a tier. It's a compiler warning at the hottest line of the program. The vacuum isn't empty. Casimir, virtual fields and light's medium. Between stars, we like to say there's nothing. But the nothing hums. Stakes first. If emptiness has structure, then our speed limit interacts with a medium, not the old ether, but the restless ground state of quantum fields. That means light's behavior, and even what we call empty, depends on how the vacuum is arranged. If C is bandwidth for action, the vacuum is the default workload, and boundary conditions are the settings file we rarely open. Action starts in 1948. Hendrik Casimir calculates that two uncharged parallel metal plates held micrometers apart should feel a force pulling them together. No springs, no charges, just the vacuum. The story runs like this. Electromagnetic fields in their ground state still fluctuate. Modes that fit between the plates are restricted. Outside, more modes dance freely. Fewer allowed modes inside means lower vacuum energy there. The mismatch creates pressure that nudges the plates together. Decades later, patient experiments with polished surfaces and exquisite metrology measure that force. It's tiny and real, the vacuum leaving fingerprints. Impact lands in optics and timing. If vacuum fluctuations can be shaped, then empty space has an effective refractive character you can, in principle, tune with boundaries and fields. In materials, polarization slows light. In vacuum, virtual pairs act like a faint, universal cloud. Tweak the environment and you tweak the cloud's behavior. That does not license messages faster than light. The front velocity, the earliest detectable edge tied to causal influence, stays chained to C, but phase and group velocities can wander in weird setups without breaking causality. And that's where curiosity finds traction. Complication arrives with the Scharnhorst effect. Theory suggests that between two perfectly conducting plates, the modified vacuum permits a slight increase in the phase velocity of light parallel to the plates, fractional, minuscule, buried under mountains of noise. Even if true, it doesn't move the signal front. It nudges the carrier's phase. Finite conductivity, surface roughness, temperature, and real-world geometry shave the already microscopic effect to dust. Engineers roll their eyes at headlines and reach for error budgets. Physicists underline a point. Boundary conditions matter. Human beats keep it honest. In a lab chasing Casimir forces, A researcher times experiments to avoid garbage trucks because their rumble ruins sub-nanometer stability. She polishes gold coatings, aligns interferometers, and learns the hard way that a stray hair can double the vacuum force. She tapes "Vacuum Hates Us" above the optical table. Across campus, a theorist recalculates boundary-dependent mode sums 3 ways, curses a minus sign, then gets the same result and relaxes exactly 1 eyebrow. Meanwhile, vacuum structure shows up in other corners. QED's renormalization tells us charge is screened. The fine structure constant runs with energy scale because virtual pairs pile up differently as you probe closer. In mighty magnetic fields near magnetars, vacuum birefringence should twist polarization. Observers are building polarimeters sharp enough to catch it. In heavy ion collisions, a short-lived quark, gluon plasma makes the vacuum look like a dense medium. Jets quench, correlations bloom and vanish. Nothing keeps behaving like something. Here, that's why this matters to our scene. If the vacuum is a medium with knobs at the edges, then C remains the hard cap on controllable action, but effective propagation inside devices becomes an engineering problem. Metamaterials already bend microwaves and steer infrared with subwavelength structure, creating paths that make waves arrive, as if a space contracted. Optical cavities with tailored mode densities can redistribute where energy prefers to sit. Squeezed light states shift quantum noise between quadratures, lowering measurement noise in one band at the cost of raising it elsewhere. LIGO uses that trick to beat shot noise. It's vacuum control softly. We can push farther without lying. Build cavities that exaggerate mode density changes, measure Casimir forces across shapes, temperatures, and coatings, map how finite conductivity and thermal photons sculpt the force. Layer squeeze states into resonators and look for front versus phase velocity games that leave causality untouched but timing cleaner. The goal isn't chasing headlines about faster than light. It's shaving picoseconds of latency and decibels of noise by treating the vacuum like a tunable environment. Microstories keep the rhythm. A grad student watches an interferometer fringe crawl by 1,000th of a wavelength and whispers, "Don't breathe." A team chasing vacuum birefringence in polarimetric data argues over a 2 sigma bump, then rejects it because the calibration sheet has coffee on it. A reviewer writes, "Define superluminal," and the authors reply with a paragraph that ends, "Front velocity remains C," in bold. Tension stays honest. The vacuum is not an ether that lets you send news faster than light. It's a substrate whose properties shift subtly with boundaries and fields, letting you root around cost inside legal physics. If C is bandwidth, the vacuum is the codec, and boundary conditions are like switching compression settings. You don't break the wall, you stop paying pointless fees at the toll booth. And that nudge sets up our next battleground. Gravity amplifies the vacuum's quirks near horizons. Thermodynamics becomes geometry. Code decides where inside lives. If nothing plays this hard in a lab, it'll play louder where spacetime bends the most. That's where budgets get tight and where the scheduler's hottest tricks show through. The opera Jolt, faster than light neutrinos that weren't. The rumor sounded like a dare, 60 nanoseconds early. In 2011, under a mountain at Gran Sasso, Opera compared proton pulses leaving CERN with neutrino detection 730 kilometers away. The plot leaned the wrong way. If true, neutrinos were outrunning light in vacuum by a sliver, about 60 ns over 2.43 milliseconds of flight time, roughly 1 part in 40,000. It wasn't a headline, it was a grenade. Here's why the room went cold. SN 1987A had already taught us messengers leave at different times and traverse different media. But Opera claimed same start gun, same finish line, neutrinos arriving early against a baseline set by the speed of light in vacuum. That's the sacred constant. Shift it and causality groans. If the number held, relativity didn't just get a haircut, it lost a limb. Inside Opera, nobody wanted to believe. They spent months trying to kill their own plot. The baseline was surveyed with geodesy to centimeters. GPS-disciplined clocks anchored time at both ends. A 1 pulse per second signal traveled through kilometers of optical fiber down to Opera's master clock. They measured delays in every module they could touch. The number refused to die. So they did the rare right thing. They went public and asked for help, with a preprint and a press conference that said, in careful language, "We can't find the mistake." Human beats made the stakes land. A postdoc at Gran Sasso refreshed an email thread like a cardiogram. In Geneva, an accelerator veteran traced timing racks with his fingertip, mouthing part numbers. A journalist rehearsed Einstein was wrong, then deleted the line and wrote Einstein under test. Inside the collaboration, arguments circled: publish and risk humiliation, or sit and risk missing the moment. They chose to stand up twice, once with the claim, once with the correction. The community moved fast. Theorists spun scenarios: Lorentz violation with energy dependence, sterile neutrinos slipping through shortcuts in extra dimensions, modified dispersion relations. Constraints snapped back. If neutrinos outran light by 60 ns over 730 kilometers, SN 1987A's neutrinos should have beaten photons by years, not hours. Cohen and Glashow sharpened the knife. Superluminal neutrinos would radiate energy via weak analogs of Cherenkov radiation, shedding electron, positron pairs and arriving smeared in energy. Opera's spectrum didn't show that. Meanwhile, other experiments, minus in the United States, Icarus down the same tunnel, tightened their timing and aimed at the same question. Then came the special run. Tightly bunched proton packets at CERN so each neutrino's birth could be matched to a narrow time stamp. Engineers hauled portable time transfer gear to remeasure delays. They sent calibration pulses along the same fibers neutrino timestamps rode. They wiggled connectors with the dread of people who know that, sometimes, it's a loose screw. It was, in part, a loose screw. The optical fiber carrying the GPS time down to Opera's clock was slightly misheated. That mechanical sloppiness introduced an extra delay, on the order of tens of nanoseconds, in the timing reference reaching Opera. Another issue pulled the other way. An oscillator used in the time-stamping chain ran slightly fast, biasing event times in the opposite direction. The two errors nearly canceled, leaving a net apparent advance near 60 nanoseconds. When they seated the fiber correctly and recalibrated the oscillator, the miracle evaporated. The microstory stung and soothed. A technician stared at the tiny ferrule of a connector and whispered, "You." A student stepped outside into cold air and let out a breath he didn't know he'd been holding. Someone wrote loose cable on a whiteboard and then under it, "We owe Einstein a bottle." The press room felt different the second time. Microphones still bright, questions gentler. The collaboration apologized not for asking, but for not catching the mundane answer sooner. The impact rippled cleanly. Opera retracted the superluminal claim. Icarus and others reported neutrino speeds consistent with C within uncertainties. The official line returned to what every high-precision field learns early. Extraordinary claims are calibration problems until proven otherwise. But the deeper lesson fit our seam. Timing chains are long. One-way comparisons lean on shared conventions and hardware honesty. A 60 nanosecond slip over 730 kilometers is a part in 40,000. That's small enough for a loose connector and a drifting oscillator to fake, and big enough to upend careers if nobody checks. Opera didn't prove faster than light anything. It proved the cost of living at the edge of measurement. It also proved a cultural point. You can be wrong in public and still do science right. The team took the heat, fixed the stack, and taught a generation to publish calibration trees like their results. Tie it back to our running story. SN 1987A showed staggered channels. Pioneer exposed the fragility of reading one-way truth from two-way tones. Entanglement forced us to separate messages from patterns. Opera tattooed, calibrate everything on our knuckles. In each case, the wall for controllable action held. The seam sat where it always was, in synchronization chains, in assumptions turned standards, in the way we map local ticks into a global script. And while the opera headlines faded, a different shortcut kept turning up on whiteboards. Don't outrun light, move the road. Geometry, not speed, as the lever. The math said you could surf space-time without breaking C. The price was steep. The idea wouldn't die. Warp bubbles without breaking C. The geometry trick. While opera's headlines cooled, a different shortcut kept showing up on napkins and whiteboards. Don't outrun light, move the road. Stakes first. Chemical rockets die on the math. Even fusion rides a budget that laughs at interstellar timelines. If geometry can do the lifting, you don't need an engine that breaks C. You need space-time shaped to carry you like a conveyor belt. That's not a fantasy line. It's a metric with footnotes and a price tag. In 1994, Miguel Alcubierre wrote down a solution to Einstein's equations that read like a dare. In his metric, space in front of a compact region contracts, space behind expands. The bubble rides that distortion. Inside, you're in free fall, no acceleration, no local speed limit broken. Your coffee still sits in the cup. Outside, distances shrink in front and stretch behind, so the cabin can cover light years in less coordinate time than a photon would need in unwarped space. Locally legal, globally audacious. Impact landed in two columns, possibility and cost. Possibility said the equations admit a geometry that carries you faster than light in the global sense without violating the local rule. Cost said the stress energy needed isn't on our shelf. You need negative energy density, exotic matter. Quantum field theory admits negative energy in tiny, regulated doses. Casimir plates, squeeze states, quantum inequalities that fence you in. You can borrow a little briefly in a small place. A starship-sized, sustained warp wall. The math turned into invoices we couldn't pay. Early estimates were brutal, galaxy-level energies in naive setups. Then smarter shaping brought the total exotic budget down Jupiter level, then less, by making the wall thinner and redistributing stress. Each improvement arrived with caveats. Thinner walls push you toward instabilities. Sharper gradients invite quantum back reaction. The bubble's front edge is causally cut off from the interior, so steering and braking become paradoxes. How do you stop a wave whose crest won't listen to commands from behind it? Human moments made the audacity feel personal. Conference hallways filled with crescents and arrows as people sketched bubbles on napkins. An engineer tucked one napkin into a notebook labeled "One Day," a private pact with math. A relativity purist spent a summer calculating tidal forces in the wall and returned with a warning. Stray too close, and your ship gets shredded by gradients you can't tame. The drive that eats its passengers isn't a headline you want to own. And yet, the geometry trick refused to fade because analog started whispering back. If we can't bend spacetime in a lab, we can build systems whose effective equations rhyme with gravity. Fluid flows over shaped obstacles create horizons for surface waves, regions where ripples can't climb upstream. Bose. Einstein condensates host sonic horizons for phonons. Optical fibers with moving refractive index fronts mimic how light stretches near a gravitational well. In these systems, Hawking-like radiation has been reported, correlated excitations in the right spectrum popping at the horizon. It's not propulsion. It's proof of principle that horizons and their thermodynamics emerge when you shape an effective metric. Engineers chase the miniature version. Metamaterials and transformation optics take Maxwell's equations and ask, what distribution of permittivity and permeability makes waves follow a prescribed path? Cloaks hide bumps by guiding light around them. Graded index lenses compress path length so beams behave as if space contracted. Phased arrays synthesize apparent motion for beams that no single element could achieve. None of this moves atoms between stars. It does shape fields to do more in less space. That's microwarp. Rewire geometry inside devices so the effective distance a wave must traverse is shorter, while the front velocity, causal action, stays pinned to C. The exotic matter roadblock stayed firm. Quantum inequalities, sharpened by Ford and Roman and others, Limit how much negative energy you can accumulate and for how long. You can squeeze light to generate local negative energy densities, but the loan terms are harsh. The more you borrow, the faster the debt collector, compensating positive energy, shows up. Proposals to amortize the cost, pulse the bubble, distribute negative energy in lattices, piggyback on Casimir-like boundaries, run into the same gatekeeper. You can borrow, but not at starship scale for mission durations. Still, the lab work isn't a detour, it's the training ground. A small group built an interferometer to hunt for tiny, engineered path compressions in glass by shaping index profiles dynamically. The result wasn't a warp signal. It was a catalog of what timing tricks survive calibration. Another team tuned a fluid flow until the analog Hawking signal appeared above background and learned noise budgeting that would make a space interferometrist proud. These are skills you need if geometry is ever going to carry anything more than jokes. Microstories kept the 30-second pulse. A young researcher in Texas presented a refined metric that cut the notional energy by orders of magnitude. Headlines sprinted past the fine print. He answered emails from school kids and retired pilots in the same night, then spent the next morning aligning a laser to measure a phase shift at the edge of detectability. Across the ocean, a basement lab caught correlated noise at a fluid horizon and celebrated like they'd seen a comet. Here's the ethical line we keep. Locally, C is the wall for action. Globally, geometry can rearrange what far means. Warp metrics respect C in every small neighborhood and violate no experiment's two-way invariance. The obstacles aren't doctrinal, they're practical energy conditions, stability, control. The takeaway you can use now is quieter and closer. In antennas, sensors, and chips, bend effective geometry to route around cost. In comms windows near planets, use curved spacetime to your advantage. In analog horizons, test how codes move meaning without couriers. Don't outrun light. Move the road where you can, test where the math is telling the truth, and keep your language honest. Geometry is the lever we can already push in miniature, and the only lever that, one day, might carry us without breaking the wall. When constants drift, variable C and early universe hacks. By now the wall looks like a budget. So here's the oldest bill in cosmology. The sky is too coordinated for the time we gave it. Stakes first. The cosmic microwave background, light released when the universe cooled enough for electrons and protons to pair up, arrives almost the same temperature in every direction. If C has always been what we measure today, then widely separated patches on that last scattering surface were never in causal contact. They couldn't share heat, yet they matched a few parts in 100,000. That's the horizon problem, and it forced a choice. Change the route or change the clock. Inflation changed the route. In the early 198s, Guth, Lind, and others described a brief period of accelerated expansion, space stretching exponentially. Regions once small enough to talk got blown far apart, leaving uniformity baked in. Inflation did more than smooth. It predicted a flat geometry and a specific spectrum of tiny fluctuations. Later, satellites, COBE, WMAP, Planck, mapped those bumps and found the pattern inflation promised. Score one for geometry. But there's a second move that never quite left the room. Variable speed of light, VSL. In the 199s and 200s, theorists asked whether the early universe could have run a different clock, an effective C larger than today's, long enough for distant regions to thermalize, then freezing to our current value before recombination. The pitch was simple: keep expansion modest, widen the causal neighborhood by boosting C, arrive at the same smooth sky. The moment you say C changed, the room fills with red pens. Units are a trap. If you just rescale meters or seconds, you've said nothing. To matter, a VSL theory must change dimensionless combinations, like the fine structure constant alpha, or embed C variation in a covariant framework that respects the symmetries we've tested. Break Lorentz invariance carelessly and you wreck particle decays, mess with atomic spectra, and lose GPS. The only versions worth attention, right, and action. derive field equations, and compute observables that could differ from inflations. Human beats kept the fight honest. A young cosmologist, tired of hearing "that's just a unit change," rewrote her model in terms of alpha, coupling a scalar field to electromagnetism so alpha drifted in the early universe and froze later. A colleague asked the only question that matters: where's the smoking gun? She pointed at subtle shifts in the acoustic peak positions and polarization patterns, differences small enough to hide under current error bars, but not forever. Constraints stack up. On Earth, atomic clocks compare transition frequencies and find no present-day drift in alpha at levels of parts in 1017 per year. Quasar absorption lines over billions of years show claims and counterclaims. The cleanest analyses favor tight bounds or nulls with slight spatial hints under debate. High-energy astrophysics slams the door on many Lorentz-violating schemes by showing no energy-dependent arrival time dispersion for gamma rays across cosmological distances. Any VSL that survives has to be early, brief, and subtle, then decouple completely. Meanwhile, inflation isn't one theory, it's a family. Some branches sprouted conceptual baggage, eternal inflation, and a multiverse of pocket universes, but the core predictions kept landing. That success raised the bar for alternatives. VSL needed crisp, risky signals. A few models suggested non-Gaussian fingerprints or specific shifts in the ratio of the acoustic peaks. The community did what it always does: wrote them down, pointed at data, and said, "Prove it." There's a middle path that reframes the debate without writing CT on a slide. In some quantum gravity-inspired pictures, doubly special relativity, or rainbow metrics, effective dispersion relations bend at extreme energies while leaving low-energy Lorentz symmetry intact. Causal structure in the primordial plasma could look different than our extrapolation backward suggests, not because messages outran light, but because light itself, propagating degrees of freedom in a hot, dense bath, had different rules. In emergent spacetime views, the effective speed of excitations flows with scale the way couplings do. The present-day wall stands. The early epoch budget was permissive. The trap you avoid is coordinate mirages. In curved spacetime, coordinate speeds vary all the time. Shout "see changed" because your chart does something weird near a horizon and you'll earn a referee's sigh. The serious attempts are covariant, match laboratory limits today, and make falsifiable claims about the early sky. Then they wait for better maps. Human micro-stories keep the pulse. A speaker presents a VSL fit to the CMB that rivals a mainstream inflationary model. Afterward, a grad student asks about predicted B-mode polarization. The answer is tiny but distinctive. Months later, a new data release narrows error bars, and the room moves on without drama. In a hallway, two physicists trade tired jokes about fashionable versatility versus unfashionable clarity, then team up on a proposal to push clock comparisons another order of magnitude, because even nulls move science. Here's what folds back into our scene. Whether inflation smoothed the map by stretching space or the early universe effectively widened the messaging budget, our present-day wall for controllable action, two-way C, remains nailed down by every test. The one-way story we tell across the sky is still stitched by Einstein synchronization. The origin story might include an early patch, route shorter, clock faster, or both in disguise. The runtime we inhabit respects the contract. The render looked different when the first frames compiled. Time slices and asymmetric reality, preferred frames quietly return. By now we've treated C like a budget and the vacuum like a workload. There's one more quiet lever we've been using without saying it out loud, a frame that steadies our hand. The theory says no inertial frame is special. Practice whispers a different kind of truth. Some frames are convenient enough to act like defaults, and convenience has gravity. Start with the sky's oldest backdrop. The cosmic microwave background is a near-perfect 2.7 Kelvin glow. Leave our motion in, and a dipole appears, one side slightly hotter, the other cooler, because we're moving through that bath at about 370 kilometers per second relative to it. Subtract that dipole and the glow goes uniform again. That subtraction defines a simple slice, the frame in which the CMB looks isotropic. Cosmologists use it every day. They call it the CMB rest frame. They don't bow to it, they calibrate against it. Here's why that matters. When we stitch distant events into a narrative, we pick a time coordinate. In cosmology, moving time tied to the expanding universe gives us a clean book. Galaxies at rest in moving coordinates drift apart with the Hubble flow. The CMB is the quietest clock on that wall. We run our ledger in that frame because the math becomes sane and the maps become legible. That's not heresy. It's a software default. But the theory's guardrail stays firm. Every local test of Lorentz invariance keeps landing null. Resonant optical cavities spun on turntables and dragged through seasons. Atomic clocks flown and compared. Gamma-ray burst photons separated by billions of years. None show anisotropy in the two-way speed of light or energy-dependent delays that would scream preferred frame in the dynamics. Within our reach, local physics refuses to pick a direction. That's the law. The CMB frame is the story we write on top. Human beats reveal how this plays in rooms where careers live. A cosmologist flips through power spectrum slides and transforms data into the CMB frame before fitting models. The way a chef salts water before pasta, it's just what you do. From the back row, a theorist raises a hand. "Aren't you smuggling in a preferred frame?" She smiles. "I'm choosing a coordinate system that the sky suggested. The invariants don't care what I call it." Down the hall, a purist crosses out "universal rest frame" in a draft and writes "cosmic rest frame," because words matter even when the math doesn't blink. The stakes sharpen when we talk about now. Special relativity warned us. Distant simultaneity isn't a fact of nature, it's coordination. In practice, we pick slices. For cosmology, that's moving time tied to the CMB. For networks, it's a realization of coordinate time tied to GPS and the Bureau International des Poids et Mesures, UTC stepping through leap seconds while proper times run on satellite clocks with relativistic corrections. In each case, a frame or time scale acts like a backbone. It doesn't break Lorentz symmetry. It makes the ledger workable. Meanwhile, tests of symmetry keep pushing. Michelson, Morley descendants with cryogenic optical cavities compare frequencies as Earth spins and orbits. Constraints on anisotropy in C tighten into parts in 1017 and beyond. Clock comparison experiments hunt for sidereal drifts that would betray a background field. High-energy cosmic rays and TV photons from flares show no consistent energy-dependent speed that would hint at broken Lorentz symmetry over cosmic baselines. The message is boring in the best way. Dynamics stay symmetric, useful frames stay useful. There are honest attempts to formalize the whisper. Einstein ether theories add a unit time-like vector field, an everywhere-present flow that defines a local rest, then let it couple weakly so low-energy physics looks almost Lorentz invariant. Horava, Lifshitz gravity breaks Lorentz symmetry at high energies to gain a renormalizable structure, then aims to recover it in the infrared. Doubly special relativity tries to keep both C and a Planck scale invariant by deforming transformations. Each is a playground with constraints that bite hard. None have dethroned general relativity. All mark a willingness to test whether symmetry is fundamental or emergent kindness. Now fold this into our scene. One-way speed and distant simultaneity are defined within a chosen slicing. In practice, we align our world with a frame, the CMB for cosmology, a coordinated time scale for metrology, then act as if that frame is invisible. It works because the invariants anchor everything that can bite us. It also hides how much interpretation lives in our choice. When entanglement coincidences are sorted, those time tags ride a network disciplined under a convention. When we say a neutrino burst arrived hours before optical light, those hours live in a global time we built. When we write page curves for toy horizons, the notion of before and after in evaporation depends on a foliation that makes path integrals tractable. Human microstories keep the beat. A student normalizes a sky map into the CMB frame and watches the dipole vanish like a smudge wiped off glass, then writes "goodbye, wind" in her notes. An experimentalist tapes up Lorentz bound improved times 10, and under it smaller, "Stop emailing me about time travel." A referee returns a paper with "replace preferred unless you mean to pick a fight," and the authors change one word and keep every equation. So here's the clean version. No lab can detect motion through a luminiferous ether because there isn't one. The two-way C stays nailed down by every test. Yet globally, for storytelling across light years, we pick slices that behave like a common clock. The cosmos even hands us one. That's not breaking symmetry, it's building on it. And in the places where budgets run hottest, horizons, networks, clocks, the difference between law and ledger is the space where a real glitch could hide. Not a faster-than-light message. A misfiled assumption we mistook for bedrock because it made the maps look good. The cover-up versus the paradigm, how truth gets misfiled. People want the staircase, the tidy step-by-step climb. Most days, science is a warehouse. Crates stacked to the rafters, labels half right, aisles blocked by projects that shipped yesterday. No villains, just forklifts and deadlines. That's where truth goes missing, not buried, misfiled. Funding shapes the floor plan. Proposals survive by promising deliverables. A map, a detection, a tighter bound. We might find something odd isn't a milestone, it's a red flag. So when Pioneer's decimals drifted or an Earth flyby spat back a few millimeters per second off script, managers asked a practical question. Will this risk the next maneuver? If not, the anomaly went into the housekeeping drawer. That drawer exists for a reason. Missions fly because someone refused to chase every flicker. Inside the buildings, the memos were sober. Thermal recoil likely explains sunward acceleration, pending improved emissivity modeling. Station handover geometry under review, operational impact negligible. Calm sentences did their job. Press offices followed suit. Headlines celebrate firsts and confirmations, not residuals that won't flat. The public saw confidence. The labs saw caveats. That gap wasn't deceit. It was inertia doing what it always does. Smooth corners until the palette fits. Over time, inertia hardens into story. Textbooks compress debates to 2 lines. A generation learns the cleaned version. 10 years later, a new analyst rediscovers a persistent wiggle and also inherits the social cost of asking about it. A reviewer writes, "Well trodden," even if the tread marks never reach the far corner. The narrative stabilizes, the curiosity narrows. We don't only miss wild new physics. We lose leverage, quiet techniques that live in the seams until someone gives them a name. Career calculus enforces the trend. A young scientist weighs 2 papers. One tightens a standard result. One explores an anomaly their advisor calls interesting but risky. Letters of recommendation flow easier from the first. The second gets whispered about over coffee, promising but unfocused. Multiply that choice by 1,000 desks and you get culture. Clever, disciplined, and slightly allergic to wrinkles it can't iron by the next review. The result is a bias toward polished nulls. Optical cavities spun under cryogenics. Null, another decimal place on Lorentz invariance. High-energy photons across billions of years. Null, no dispersion you can hang a theory on. Those are victories. They narrow the map and teach our instruments discipline. Anomalies aren't so clean. They live in calibration trees and firmware notes, in logs that remember which technician swapped a board at 3 a.m. to make them publishable. Somebody has to do heroic accountancy. Bake tapes, reconcile epics, annotate every connector. That's not glamorous, and it's hard to fund unless you promise a payoff you can't promise honestly. So truths slip through cracks not because hands pushed them, but because hands were full. A mid-level analyst drafts a note. Post-fit residuals exhibit sidereal modulation. Her lead says, "Great appendix, keep the main text on performance." He's protecting scope. She files the note. Weeks later, a senior scientist reads to the appendix and asks for the raw logs. Most stories like this end with a coffee and a shrug. Sometimes coffee opens a drawer. Whistleblowers don't fit here. There's no crime, only gravity, of consensus, of schedules, of reputations. The same gravity that keeps clocks honest also rounds language. Defined by convention becomes defined, full stop. Small edits, big drift. We're not talking about a plot to silence weirdness. We're describing a machine that rewards clarity so aggressively that it trims ambiguity until you forget where the choice lived. The cure isn't chaos, it's ritual. Publish calibration trees like results. Make anomaly budgets part of every spec. What size of residual merits a task order, who owns it, how long it gets before the drawer. Fund boring metrology with the same pride as shiny detections, because the next breakthrough will look like a stability plot that stops drifting. Treat messy figures as living documents, not embarrassment. If an effect dies under a better model, write its obituary with the same care you'd write a discovery. What it taught, how it fooled you, where the demon hid. Micro-stories make the fix human. A data archivist begs for money to migrate decaying mission tapes. She's told to find a science case. She writes one word: recovery. It doesn't land until a private foundation treats the archive as cultural heritage and pays to rescue it. A theory celebrity posts a flashy preprint tying 3 anomalies into a grand crack. It blows up online, then deflates under cross-checks. The lab that could arbitrate stays quiet. Their charter is operations, not controversy. Meanwhile, a small group in a basement rescues a timing dataset, finds a systematic everyone assumed away, and posts code with the plot. The email they get is short: "Thank you, we've been seeing this for years." Here's the turn that matters for our story. If the wall is a budget and the seam is a convention, then anomalies are the smoke tests for the architecture. They don't license fantasies, they force better contracts. Pioneer didn't break gravity, it taught us to count photons of heat. Opera didn't outrun light, it taught a generation to seat fibers and distrust pretty plots. Entanglement didn't violate causality, it split messages from patterns and gave us a business model for quantum networks. Each time, the scandal wasn't a cover-up. It was drift, the distance between what the equations guarantee and what the language pretends. So we stop pretending. We write the contract on the board where everyone can see it. Two-way C is invariant. One-way synchronization is a definition that works. Entanglement installs structure you can only read with slow notes. Horizons enforce budgets with code, not couriers. The vacuum is a medium you can nudge without cheating. Then we promise to publish the seams. Because when the first real fracture shows up, and it won't arrive as a press-friendly eureka. It'll be a residual that refuses to flatten, and a few people who decide not to file it under later. That's not a cover-up. That's the moment a paradigm remembers how to change. The glitch plainly stated what we can say, what we can use. Here's the clean version without smoke or hype. The speed of light is a hard budget for controllable action. Anything you decide at A and want read at B, every round-trip test nails that to the wall. The glitch isn't a tier in physics. It's a seam in how we coordinate clocks and a set of legal maneuvers. Geometry, encoding, environment, that route around cost without breaking causality. If you want what's usable, it lives in those 3 buckets. Geometry first. You don't have to outrun light if you can shorten the path your signal experiences. In practice, that's transformation optics, graded index media, phased arrays, and analog horizons. We already fold electromagnetic distance with metamaterials. Cloaks guide waves around obstacles. Grin lenses collapse path length. Reconfigurable surfaces steer beams so the effective route gets cheaper while front velocity stays honest. Inside instruments, microwarp is real. Engineer fields so the phase advance per unit length rises. Shave time of flight inside cavities. Compress multipath in antennas. On mission scales, geometry becomes ops. Plan deep space optical links to skim gravitational wells when Shapiro delay helps scheduling. Align windows so curvature bends paths into your budget. None of this breaks C, it makes distance negotiable where it matters. Encoding second. Entanglement isn't a courier, it's scaffolding. You pre-install correlations across a network, then spend them when a classical message, paying the C tax, arrives. That turns instant looking into a product roadmap. Quantum key distribution to detect eavesdropping by error rates. Teleportation to move states without moving particles. Entanglement swapping to stitch long baselines from short, enabling repeaters. Treat bell pairs like cash. Stock them during quiet periods, consume them on demand, keep fidelity above threshold with purification. The service level language matters now. Pairs per second, end-to-end fidelity under loss, uptime across weather. No signaling faster than light ever, but meaning lands like you cheated because the pattern was pre-compiled. Environment third. The vacuum is a medium you can lean on. Casimir forces prove boundary conditions rewrite mode density. Squeezed light proves you can reassign quantum noise. Vacuum birefringence near magnetars tells you polarization responds to strong fields. In labs, build cavities that exaggerate mode shifts. Use surfaces and temperatures that make tiny forces predictable. Inject squeezed states to lower measurement noise while respecting front velocity. The Scharnhorst calculation remains a curiosity. Phase nudge, not signal, buried under real-world losses. The usable lesson is calmer. Design the nothing inside your device so it wastes fewer ticks. Now put guardrails in big letters. 3 tests kill hype: front velocity, controllability, reproducibility. If the earliest detectable change at B doesn't beat C, you didn't send FTL information. If you can't decide the content at A and have B read it without a classical side channel, you didn't message. Entanglement alone doesn't count. If the effect collapses under tighter timing or cleaner calibration, you measured your eagerness. These rules aren't style. They're the border between engineering and fantasy. What about the famous anomalies? Treat them as design notes. SN 1987A. Staggered messengers teach you channels have different buffering. Don't infer vacuum rules from trapped photons. Pioneer. Two-way Doppler is a polished interface. Map every watt of heat before you rewrite gravity. Flyby residuals. Station geometry and Earth rotation can masquerade as physics. Model handovers like they're science, not housekeeping. Loophole-free bell tests. Separate patterns from messages. Enforce independence of settings and honest clocks. Opera. Publish the calibration tree with the claim. Seat fibers. Double-check oscillators. Invite replication before headlines. Here's a concrete playbook you can fund. Analog horizons. Build BOS, Einstein condensate and optical fiber platforms where effective surface gravity is tunable. Target Hawking-like correlations with spectra, phases, and page-like turnover when coupled to engineered reservoirs. The payoff isn't poetry. It's a training ground for correlation extraction and timing discipline. Vacuum engineering. Map Casimir forces across geometry, conductivity, and temperature with metrology-grade surfaces. Publish code and error budgets. Layer squeezed states into resonators to test front versus phase behavior that leaves causality untouched but improves timing and sensitivity. One-way timing stress tests. Deploy city-to-regional optical clock networks with stabilized fiber and free space links. In controlled subsets, adopt non-Einstein synchronizations and close operational loops, navigation, phase tracking, to audit how conventions propagate. Two-way C stays sacred. The goal is flushing hidden assumptions before they bite deep space. Quantum networks. Stand up entanglement services with SLAs, bell pairs per second at target fidelity, expected uptime, attack models. Implement device-independent tests to force honesty from black boxes. Treat entanglement like cash, not magic. Geometry in devices. Use transformation optics and reconfigurable metasurfaces to compress path length, tame multipath, and synthesize motion in beams. Measure latency gains that survive calibration and publish front velocity checks in bold. Keep the language clean. Two-way C is invariant, nailed by resonators, time of flight, and every round-trip test worth trusting. One-way C equals two-way C by definition, Einstein synchronization that makes the world computable. No signaling stands as long as independence and space-like separation hold in your setup. Horizons enforce budgets with code, entanglement wedges and islands, not couriers. The vacuum is a tunable environment with small legal levers. Human scale counts. Most winds will look like an ugly plot that stops drifting, a femtosecond shaved, a decibel of squeeze held through noon, a sidereal modulation that finally dies after a firmware patch. Celebrate those, they're the bricks. When the first fracture worth headlines arrives, it'll pass the guardrails and come with data, code, and a calibration annex thicker than the paper. The wall will still be there. We'll just be working around it with fewer wasted ticks. What this says about us: consciousness, clocks, and render budgets. Attention pulses in frames. Awareness budgets updates. Memory compiles our continuity. The roadmap tests risks and the next 20 years. So what do we actually do with this? Stakes first. Pick the wrong questions and we burn decades on clever dead ends. Pick the right ones and we turn the scene, geometry, encoding, environment into tools. The winds won't look like sci-fi. They'll look like timing links that stop drifting, quantum services that keep working in bad weather, analog horizons that deliver the exact correlations the math demands, and a culture that publishes calibration trees with the same pride as detections. Start with horizon analogs, the safest way to stress the scheduler without touching real spacetime. Build platforms where the effective geometry is in your hands. Bose, Einstein condensates with tunable flows that create clean sonic horizons. Optical fibers with engineered refractive index fronts that act like moving boundaries. Water channels shaped to make surface wave horizons that are stable longer than a lab session. The test isn't a headline, it's precision correlation. Hawking like pairs with the right spectrum and phase relations, under knobs you can scan. Couple these horizons to engineered reservoirs and watch for page-like turnover in toy entropy curves. If the entropy bends at the right time, you've shown that code, not couriers, moves meaning across a render boundary. That's a design lesson, not a metaphor. Meanwhile, vacuum engineering moves from thought experiment to calibration target. The Casimir force is our handle. Make it practical. Map forces across varied geometries with metrology-grade surfaces. Calibrate finite conductivity, temperature, and roughness until the prediction and the measurement agree within stated uncertainties. Publish the surfaces, AFM scans and the codings, ellipsometry right beside the plots. Then start layering on quantum states. Inject squeezed light into high-Q cavities and measure how phase and front velocities behave inside real, lossy devices. The rule is simple: nothing faster than the signal front, and any phase tricks must pay back as lower latency or lower noise in an instrument. When you shave a picosecond from a path because your mode density was designed, not endured, you've turned the vacuum into a component. Third, stress one-way timing on purpose. Everyone parrots the line that we've never measured the one-way speed of light without convention. Fine, turn that into a test bed. Stand up a city to regional network of next-generation optical clocks, lattice clocks and trapped ion clocks, linked by stabilized fiber and free space paths. In controlled subnets, adopt non-Einstein synchronizations and then close operational loops, navigation solutions, phased array coherency, interferometer phase tracking. The invariants don't move, but the exercise flushes hidden assumptions before they bite deep space tracking or interplanetary laser links. Publish the datasets raw, the synchronization choices explicit, and the loop closures visible. If a demon hides in how we set distant clocks, this is how you catch it. Quantum networks are the fourth pillar. Treat entanglement as bandwidth you pay for upfront, then spend with a classical sidecar that obeys C-build services, not DMOS. City-scale fiber links with satellite relays bridging weather. Repeaters that actually purify and extend pairs beyond a clean rack. device-independent protocols, so black box hardware is forced to be honest by its statistics. Track your network like an ISP. Bell pairs per second at target fidelity, uptime across seasons, attack models survived. Teleport states between nodes routinely, not theatrically. The payoff is FTL magic. It's a day when a classical network engineer treats your entanglement cache like CDN per fill. Pre-distribute structure on Sunday night for a Monday morning rush. Geometry inside devices is the quiet fifth front. Use transformation optics and reconfigurable metasurfaces to compress path length, tame multipath, and synthesize motion in beams. Phased arrays already fake trajectories no single element can produce. Push that. Graded index media already collapse travel time. Make that reconfigurable in situ. In antennas, design field distributors that turn cavernous apertures into thin panels without losing coherence. In sensors, target time of flight compression that survives calibration and front velocity checks. The metric you care about is latency that doesn't vanish when you tell the system the truth. Gravitational assists for information are the sixth, slower burn. We already sling spacecraft with gravity. Sling bits the same way. Plan deep space optical links that graze potential wells to buy schedule flexibility or signal to noise in the margins. Test frequency standards that stay coherent while a signal rides a Shapiro delay near a limb. It's not a warp drive. It's an ops manual that treats geometry as a friend rather than an obstacle. Now the risks, the ones that kill trust faster than any error bar. Hype is a recurring predator. A single lab plot can metastasize into C is broken across 1,000 thumbnails. Draw 3 red lines and keep them in every slide deck. The front velocity is the arbiter. Controllability defines messaging. Reproducibility is non-negotiable. If the earliest detectable change doesn't beat C, you didn't send faster than light information. If you can't decide the content at the source and read it at the destination without a classical path, you didn't signal. If it collapses under cleaner calibration, you measured your eagerness. Military interest will arrive early. There's money there and silence. Take the resources but negotiate delayed, complete releases when safety isn't at stake. Proprietary black boxes corrode trust, so do trust us plots. If a result can't survive code release and independent replication, it doesn't belong in this story. Build ethics into proposals, anomaly budgets, release schedules, and a commitment to publish calibration trees with claims. Culturally, we fix drift with ritual. Make anomaly budgets as normal as power and mass budgets. Define thresholds that trigger a task order and the time box for chasing it. Reward boring metrology in tenure letters and grant criteria. Fund archive rescue like you fund new detectors. The next fracture might be stuck on a decaying tape. Normalize ugly plots early. If an effect dies under scrutiny, write its obituary with lessons learned and the calibration demons you found. Students learn from those the way they learn from discoveries. And keep the human pace in mind. Most wins will be small and stubborn. A femtosecond of jitter removed, a decibel of squeezing held through lunch, a sidereal modulation that finally disappears after a firmware patch. Celebrate those. They're the bricks under any headline you'll actually trust. The first true fracture worth attention won't look like a sci-fi reveal. It'll be a residual that refuses to flatten after every honest attempt to kill it, passing the 3 red lines with code attached. Benchmarks keep us honest. For analog horizons, reproducible hawking like correlations with tunable surface gravity, and a clear, independent verification of page like turnover in a toy system. For vacuum engineering, a public library of Casimir force maps across geometries and temperatures, with surfaces and coatings characterized to within their noise, plus the first sensor that beats a competitor because the mode density inside was designed. For one-way timing, a public dataset where rival synchronization conventions are applied to the same network and operational outcomes, navigation, coherency, are compared in the open. For quantum networks, a cross-country entanglement service with SLAs and a device-independent test suite that an adversary can't fake. For geometry and devices, latency reductions that survive front velocity checks and show up in real deployments, not just benchtop DMOS. If you need a 20-year picture, years 1-5 build the platforms and the culture, analog horizons, timing testbeds, open calibration. Years 5-10 deliver the first operational payoffs, entanglement services that don't blink, sensors that win on vacuum design, geometry compressed comms in the field. Years 10-20 push endurance and scale, networked horizons as simulators for gravitational thermodynamics, interplanetary optical links that treat curved spacetime as an asset, device geometries that make distance negotiable in silicon. All the while, keep the contract visible. Two-way C is invariant. One-way conventions are definitions, no signaling holds. Horizons move meaning with code. The vacuum is a medium you can nudge. That's the map. Walk it with your language clean, and your plots ugly until they're ready. Resolution and broader meaning. The wall didn't fall. It turned into a budget, and budgets can be worked. If you want to see where this becomes hardware, subscribe and watch the tabletop horizon we're building next. The first fracture won't look dramatic, and you'll want to catch it the week it lands.